So I think that not all, but most people who would say they subscribe to some Copenhagen type ideas. I mean, a lot of physicists, I would say the majority of physicists, if you ask them, will say, if you ask them what interpretation of quantum mechanics do you subscribe to, they'll say, oh, Copenhagen or something like that. Maybe not at a Foundations of Physics conference like this one, but sort of in the general population of physicists. And people think that this kind of interpretation is built on a very sort of concrete empirical idea, which is the idea that, when we make a measurement, something really happens. So, detectors really click. When you hear a Geiger counter making a click, that's something that really happens. And the whole interpretation is supposed to be based on that kind of empirical fact. Okay, so the idea that there may be no objective facts of the matter about what's going on in the microphysical world, but when you hear a detector click, that's really some fact. That's an objective fact. I think that's what most people who say they subscribe to Copenhagen believe. We'd have to do a survey to check whether that's really the case. So
it's viewed as a very sober sort of interpretation.
Yeah, compared to some of the interpretations which say, Copenhagen does say some crazy things about microphysical reality, but when it comes to the macroscopic reality of everyday existence, it's supposed to be very sort of has its feet on the ground, and it's supposed to be, not denying the facts of everyday existence. Whereas if you look at something like the Everett interpretation, it says
the many worlds
type interpretation, it says, okay, fundamentally reality is completely different from what we think it looks like, and this classical reality that we see is some kind of emergent, fuzzy type of phenomenon, and on the face of it, that seems like a much crazier type of position to take. So the dirty secret in the end is that it can't be that simple, right? You can't just have facts of the matter about what detector clicks are, at least if you also want to say, and I think most people do want to say, that quantum mechanics is universally applicable, right? So if you want to say that actually quantum mechanics is the fundamental theory, there's no division between systems in the world which are classical systems fundamentally and quantum systems, everything's quantum, right? Then you're going to end up in a contradictory position. This year, back in April, there was a preprint on the archive from Frauschiger and Renner, and they have proved a result which shows that this sort of naive kind of Copenhagen view doesn't really work. So what they showed, what they think they showed and the way I interpret it are a bit different. But I think the important thing they've shown is that if you want quantum mechanics to be universal in this way, then there can't be an objective, observer-independent fact of the matter about whether or not a detector has clicked.
Right.
Okay. It has to. If you want to take this Copenhagen position seriously, it has to be that whether or not there's a fact of the matter about whether a detector has clicked, it depends on the observer. So, if the sort of classic example of this is what's called the Wigner's friend experiment. So it's kind of a variant of the Schrodinger's cat paradox. But the idea is that Wigner has a friend who he puts inside a box with a quantum particle, say a spin-a-half particle or something. The friend inside the box makes a measurement. Wigner hasn't opened the box yet, right? So you might want to say, and probably most people who advocate Copenhagen type ideas would want to say, okay, that friend in the box has really made an observation, right? So you might want to say, okay, there's a fact of the matter that he's observed something and about what he's observed, but it's just that Wigner doesn't know that yet. Okay, what this result shows is that you can't consistently maintain that. So it's you can say that for the friend there's a fact of the matter about what he's observed, but for Wigner, it's not just that he doesn't know it, but for Wigner there is no fact of the matter. So this conclusion, I say, means that these Copenhagen type interpretations have to be perspectival, right? So what this means is that what's real depends on your perspective, where you're situated, right? So what's real for the friend is not the same as what's real for Wigner. So it's very important that this doesn't mean that it's real, that it's objectively real, and Wigner doesn't know. That position you can't consistently maintain here. Now, of course, one way you could get around this is by denying the universality that I mentioned. So
that it doesn't apply. So letting go of the assumption that quantum mechanics is universal.
Right. So if you say I don't think quantum mechanics applies to every system in the universe, then you'll get around this conclusion. So then you have to say, okay, what doesn't it apply to? And you might want to be sort of very empirical about that and just say it doesn't apply to things that I call measurements, right? So this would lead you into sort of a very sort of strongly operationalist type of picture of quantum theory, where you really, the whole thing is really saying virtually nothing about reality. But it's a bit of an uncomfortable situation, because then you have to say, well, what makes something a measurement and something else not a measurement, right? Measuring devices are just physical systems. So it seems like if you take that position, there's something missing, which is sort of a criterion for what constitutes something that you're not going to treat quantum mechanically, right? It seems like you're saying that there's, there must be a physical fact of the matter that some systems aren't quantum, not just sort of a matter of, for all practical purposes I can treat it as classical, but really fundamental. Because if it was just a question of for all practical purposes and the system really is quantum, then you're going to be led back into these kind of contradictions. So that's a coherent position. I imagine that probably some physicists would take that position, but it doesn't seem very appealing to me, because if all I cared about was for all practical purposes, then I would be done before we start. But part of the reason for studying the foundations of quantum theory is that in the history of the foundations of quantum theory, things that people originally thought were crazy thought experiments that would never be done, well, we're doing those kinds of experiments now. So although the whole result is based on a thought experiment which is extremely impractical, at least if you're like a physicalist, materialist, you think that there's no sort of special magic about being an observer, it's totally conceivable to do this kind of experiment, and I'd make a bet that we could do it eventually, because usually when we think of crazy thought experiments in physics, they eventually become real experiments.
Yeah.
Actually, sort of the category of thought experiment doesn't make a lot of sense to me. It just means an experiment that we're very far away from being able to do.